Since last week, I started introducing the Python functions. Okay, we have seen the concept of function, and which are basically a reusable block of codes that can perform specific tasks, and they are useful to organize the program and avoid repetition. They also improve readability and maintenance of the code, as we have seen last week. And in Python, I emphasize on the three types of function that we have in Python. The first type of function is the built-in function, which are available in the Python standard library. They're available in memory as soon as you load the Python interpreter. The second type of function in Python are functions which are defined in the built-in module. So the Python standard library has several modules that define a group of functions. In contrast with the previous type of built-in function, module-defined built-in function are not available in the working space unless you import them in memory and use them. To import the module-defined function, you have to use the keyword import plus the name of the function you would like to import. Last but not the least, we have user-defined functions. These are the types of functions that you can personally design and implement custom logic in the program. I've defined the syntax of using user-defined function that can be defined using the keyword def, and then you can implement your function as we have seen last time. For the function naming, there is a way to name the functions, which is similar to any identifier that can be used to identify an object in the Python domain space, which should be a unique name. It shouldn't be one of the Python keyword, okay? So today, I'm going to cover particular types of functions, which are called recursive functions in Python. The main purpose of this module is to help you understand that complex problem may have difficult solution, but the main solution to this kind of complex problem can be expressed as a simple recursive solution. So the accumulation of all small solution you can give to the smallest problem of the bigger one can contribute to the main solution. So those are kind of simple sub-problem solutions, but they can be used recursively to solve the main complex problem. The main purpose is to help you learn how to formulate a problem solution in terms of a program that can be recursively executed. And the next one is to help you understand the three laws of the recursion. For a problem which has a recursive solution to be implemented in Python, they have to follow the three laws of recursion. Then we should be able to understand the recursive solution as a form of iteration. We have seen how to implement iteration in Python using loops, such as for loops and while loops. This will help you understand the recursive solution you will build for the complex problem, and then you can now implement the formulation of your solution to the given problem using Python. So we'll see how we can implement those kind of recursive logic using Python as a programming language. In computer science, recursion is a method, okay, which is used for solving computational problem, where the solution can be depending on solution at the small scale or small instances of the same problem. You remember in the types of problem solving, I've mentioned one of the type of problem solving that was divide and conquer. You have a big problem, you can break down the problem in small solution. If those small problems are of the same type, you can use a recursion to resolve each type of data sub-problems. Like here on the left, you have a big problem that has been defined as a recursive solution, where you have the smallest solution here, start from the smallest, and it will be recursively used until we address the overall complex problem without any difficulty. But the big issue is how to find the relationship between those sub-problems in order to use the smaller instance of the problem to solve the all bigger problem. So like here in the figure, here in the middle, you have this triangle pattern. So in order to draw such kind of triangle pattern, you have to combine several small triangles and then repeatedly repeating the same logic. This will help you to build this pattern, and it's kind of a recursive problem. Same for a tree. You have a tree which is based on composition of several small components like leaves. You can see for you to draw the leaves, each branch has leaves. So you can repeat the same thing to connect those leaves. Those can make the pattern of a tree. So these are kind of illustration of recursion problems that can be resolved. So the power of recursion is its possibility to define infinite set of sub problems solution by infinite statements. Like you have a situation where you have to repeat the same process again and again. You can just define the process using some representative cases, and then this representative case will be reused again and again until you solve the whole problem. This is the power of recursion, especially when we use it in computer science programming method or technique. Let's now contextualize the definition of the concept of recursion in computer programming. So the recursion is just a programming technique where a problem or a program can be divided in subroutine like functions. This function can be calling themselves in order to resolve problem that we are intending to address with the program. So this technique consists of breaking down complex problem into smaller one, which are more manageable as a sub problems. They should be of the same type. Solving each sub problem will be contributing to the main solution. So this is how we can understand the concept of recursion in programming. So this leads me to the definition of a recursive function. Is just a function which is used to break down the main problem in smaller size of the same type, and then this function can be reused anytime we would like to get a solution of that types of problem. So we can just call it recursively within the body of the function itself or outside of the function itself from the main program or from another function. I will illustrate such three cases when I will be classifying the types of recursion. So when and why do we need to use recursion? This can be a question that you may have in your mind. Use recursive function when we have a task that can be defined in terms of a similar subtask, okay? A big problem which can be containing a subtask of the same type. In such kind of situation, you can use the recursion. And in the case where we have a problem which can be naturally recursive, such as the factorial problem or the Fibonacci number series or traveling a tree, like I've shown in the previous slides. So in some case, when you want to write a modular, clear, and elegant codes, you can also use recursion. But remember that the recursion is quite of requiring a lot of resources. So it's quite expensive in terms of memory and computation. So it's less efficient. So you have to know when to use exactly the recursion. For you to use the recursion, there is a bunch of things that you have to satisfy, like the 3 laws of recursion I will introduce now. So in Python, a recursion or a recursive function must satisfy to the 3 laws of recursion, which are the following. The problem or the function has to include a base case. What does it mean, base case? Is the condition where the recursion stops. because we need to reach, you remember when we introduced the concept of algorithm, an algorithm should have an end, okay, not run infinitely. And on the other side, we need a recursive case. So the recursive case is cases where the function call itself with a smaller or a simple inputs. Then we have the last one, but not the least, is the condition for unintentional cases. This is also important to check the inputs validation. So these are the main three laws that we need to satisfy in order to define our problem as a recursive solution and using the recursive functions. So here is the syntax to define a recursive function. It's like any normal user-defined function where you use the def, you use def keyword, and then def keyword should be followed by the name of the function, and then you have parentheses. In the parentheses, you have to provide parameters which will be receiving the argument when the function will be called, and the header of the function line will be ending with column. The column say that this is kind of a multiple line instruction. Everything coming after this column will be indented. So that's why you can see here you have the indentation, and then you have the body of the function where you need to set the base case and the recursive case. So if the base case condition is met, you will return the result. This will be the base case. Else, when the base case condition is not satisfied, you will go to the recursive case where you call again the function itself and then sending the argument for the function to be executed again and again until we reach the base case that will help us to exit the function, which is recursive function. So this is the syntax of a recursive function. Let's see now with a few examples. The first case, okay, of problem that require a recursive solution is like the factorial problem. Okay, with the factorial problem, we have a factorial formal definition say that the factorial of n, which is notated like n with the exclamation point, is equal to n multiplied by n minus 1, n minus 2, until we reach 1. So this is the formal specification of the factorial problem. So this can also be expressed as follows. The factorial of n is equal to 1 when if n is equal to 0, and is equal to n factorial n minus 1 if n is greater than 0. So we'll be repeating this second case until we reach the base case, which will be n equal to 0. That will give 1 as a result and will be the exit point from the factorial function. So let's now see how we can implement this mathematically defined function into a Python function. The mathematically defined factorial function can also be implemented in Python using this factorial function. Here we define the function called factorial of n will be given as a parameter. And then if the n is equal to 0, or the value of n, this say that if the value of n is different to the n which has been defined or sent previously as an argument, in this case, we can say that this is not defined. But if else, if n is equal to 1 or n is equal to 0, this will be the base case. So that means we have to exit the function. So in the other case, we will be going to the recursive case where we will multiply n with the factorial of n minus 1 again and again until we reach this case, which is called base case. So this is the definition or the implementation of the factorial recursive function in Python. Here is Anaconda. I will launch the notes book. Okay, this will pop up in the browser like this. So before I prepare that, let me first explain through this simulation I've provided here. I'm preparing the notebook file to run the code. So here you can see the function we have defined here will be called for the first time when we provide the for as argument. This function will be called here, and then at this time we will check this condition whether 4 is bigger than 0. That is true, and then 4 is different to n, which is not true. But since we have or here, it will go to the next case where we will take n, which is the value given from the argument 4, and then we will call the function again with the argument that will be n minus 1, that will be 3. So this will go again here. This 3 will be passed here as the argument 3. Again, we will check whether the condition we have specified is satisfied. We will go to the else case. 3 is different, is not equal to 1, and then is not equal to 0. So that's why we go to the recursive case. We'll take 3 and then multiply with the function of n minus 1. We will call again the function that will be executed here. We have again 2, which is bigger than 0 and is different to 1. So we use 2, and then we call again the function with the new argument that will be 2 minus 1, that will be 1. So for the last time, we'll get 1. 1 is greater than 0 and is different to n. So that means we'll go to this line again because in this case, this line will not be accessible. Why? Because in this case, 1 is equal, n is equal to 1, and is not equal to 0. Since n is equal to 1, in this case, we'll return 1. This will be the exit of our recursive solution. So here is the way of solving the recursion problem using Python. When you run, you will see the result is 24. So you can also try to visualize this using the Python visualizer I introduced last time. When I run this program, look at now the behavior of the program. So you understand why we say the recursion is quite expensive in terms of resource usage. For the first time when the program is launched, the Python interpreter index point will be pointing on the first line, and then it's acknowledged that it's a function definition. Then it will go directly to the body of the program. It will go to the line number 10. You will see this factorial n, at the moment this interpreter was pointing on the line 1, it acknowledged the function. That means it will store the logic of the function in memory. If there are variables that have been initialized, it will automatically initialize the variables in memory. Then it will go to the body to find the first place where the function will be called for the first time. Okay, so when I run again here, you will see in this line factorial has been called with the parameter value which is sent to the factorial as an argument, 4 will be passed to n. Next, you will see in memory now I have n which is equal to 4. And this value has been passed to factorial, which is the function which we loaded before in memory. So the CPU knows already what will be the next step, because everything has been defined in the function before. So next, you will see we go to the second line this time, and then it will check whether the value that has been sent satisfied the conditional statements. You will see it doesn't satisfy. It goes to line 4. It skipped line 3. It will go to elif, and then it will check whether 4 is equal to 1 or 4 is equal to 0. It doesn't satisfy. It skipped line number 5, and then it will go to line number 6, which will be pointing to line number 7, where we return the value of n multiplied by the factorial of n minus 1. That means we call again the function to process the second step value. You will see here the intermediary value here is still 4 for the first step, and then we call again the function here, functional, we pass the value of n, which is equal to 4 minus 1. You will see here we have 3. Then we'll go again to the same process until we reach the exits condition. You will see here now I'm at the return with the value of n equal to 2. The return value will be 2, and then the return value 2 is equal to this n we return, and then we compute again the factorial. Now we return this value because it's an intermediary value. So we try now to collect all the intermediary values and then send back the final response to the body that's called the function. And then you will see here the result will be shown as 24. So this is kind of problems that are recursive in the structure. So they have some sub problems which are same. Instead of implementing again and again the same code, you can just build a recursive function. You just have to call the function and get the results. So we can also improve that by showing intermediary values as I've shown in memory. If we don't implement the mechanism to collect intermediary values, you will not be able to get that. Like in this example, I put this print here before the return instruction to collect the intermediary values, this line. This is the main difference with the previous version. So I would like to get all steps, okay, intermediary values. So with this, you will see the result will be like this. I will collect the value of n multiplied by n minus 1 minus 1 minus 1 until I reach 1. Then I will print the final result as follow. When I check that with this new version, you will see I collect all intermediaries status of the function execution. And then when it reaches the final exits condition, which is the base case, it will return the final result, which will be collecting the intermediary result, which will be multiplied as follows. Another example is for this kind of problem of calculating the sum of a list of numbers. Let's say the problem has been formulated as follows. Compute the sum of lists of numbers such as 1, 3, 5, 7, 9 using a recursive function. Okay, so for us to formulate the solution of this problem as a recursive solution, we have to redefine this problem from adding a list of adding pairs of numbers. Okay, so this can be expressed as follows. So we have two elements of the list that can be added recursively. So it will be like 2 plus 1, and this result will be to this result we will add 5, we will add 7 and 9. So this is a kind of mathematical expression of this problem. So the interpreter will be understanding this expression depending on the priority of operators we have seen earlier in this class. So this can be expressed in the other way around, like you can just start from the last elements. You can sum them, and then you increase with 5, we increase with 3 and 1. So after getting the formal expression of the given problem, that means I have already the algorithm to solve the problem. So the problem will be to build a function that will be calculating the total of this expression gradually. So it will start from the first expression, and then it will be collecting all the intermediary values. This will help them to contribute to the overall solution. I hope it's clear. So after understanding the problem, I can now build the problem solution using Python as a programming language, and then ask the computer to do that for me. So far, I was just trying to build the algorithm, okay, to figure out how to solve this problem. Before you solve the problem, you have to understand it, okay? I understood the problem, I formalized the problem, and I get the mathematical expression of the problem. I figured out that this problem can be broken down on a smaller problem, which can be manageable, and they are problem of the same type. So this is enough for me to decide which implementation approach I have to choose. Definitely, I will use the recursive implementation approach. I will build a recursive function. So here is the recursive function that will be used to solve this problem. The function name is list sum. So the list sum should get the list of numbers, okay, as a parameter. And then it has to check the length of the list. If the list has only one element, in this case, it will be the exit case, okay? It will be the best case. If the list has more than one element, it will go to this else case, and then it will take the first element of the list, and then to that it will add the function of the sum of the remaining element of the list. That means I will call the list by sending the parameter of the next element of the list again and again until I will reach the last element of my list. So this is the function definition. And then to use the function, I have to call it. This is the body of the program from where I call the function. So the function will be called here. So I format the output printing while calling the function, because the function will be sending back the result. So I cannot do that in a different instruction. That's why I combine the way I would like to print the results. The result should be printed as sum of, I show the list of numbers is, then I call the function. Here's the function call. This function send the lists of numbers as arguments to this line. So by collecting this list of numbers, it will be running again and again, going through the function lists. Here we have the source. Here, when I run this code, you will see the result will be like sum of the list of 1, 3, 5, 7, 9 is 25. So I just copy and paste the code in this code visualizer. You will see for the first time, the pointer will be pointing on the first line, okay? Then next step will be to the body of the program. This first step is the acknowledgement of the function definition. It figures out that is a function def, and then it will store the function codes in memory. So whenever the function will be called, it will send the parameter to this function in memory. It doesn't have to read it again and again. So The second step will be now to go to the body, find the place where the function is called. It goes from line 1 to line number 8. Then next will be to get the arguments that need to be sent to the function. You will see here, num list is a list of objects of type integer. You can see this object has five items, and to access to each items has an index number. The first element will be accessible with the index 0, second element with 1 until to n-1. Okay, you remember Python is counting by default from 0 to n-1. Then after collecting the argument and send the argument to the function, it will be now running the function. It will go to the line 2. Line 2, it will check whether the condition is satisfied. We have more than one element. It will go to line 4, else. And then it will retrieve the first element of the list, okay? The current list, because the list will be shrinking, okay, for each iteration. So this time, the first element will be 1. It will collect 1. And then plus lists of the remaining from 3 to 9. Next, you will see here the list has been shrink down. This is the new list when we call this second part of the function. Again and again and again until we reach the last element of the list. You will see here now, at this stage, this is the case where we just have 2 elements from the list. So after running this round, you will see the first element will be 7 plus 9, which will be the remaining, and it will satisfy, in this case, the exit condition. Okay, you will see now the list send 9. Now the list has only one element. It will satisfy this condition. When I hit next step, you will see it will now collect the results of that step. It will be 16. And then going back to the previous results, which were provided intermediary, you will see it's also cleaning the memory. That's why we say Python is a garbage collecting language. And then finally, it gives back the results, which is 25. And you can see we clean directly the memory without leaving anything behind. So this is quite practical for problems which repeat again and again. You don't have to write several the same codes, which will be messy. Another type of recursive problem is the Fibonacci sequence number. So what is called Fibonacci sequence number is a problem which is consisting of generating numbers which are related as follows. You have the next number which is equal to the sum of the previous number. You have 0, it starts with 0, 1, and then 1. The next will be the sum of the two previous number. 1 and 1 will give the value of the next number. The next number will be the summation of the two previous number. 1 plus 2, it will be 3. The next number will be 2 plus 3 until you reach the value of n, which will be given by the problem statement. So this problem can be mathematically expressed as follows. The function of Fibonacci that will receive the value of n should be equal to Fibonacci function n-1 plus n-2 until we reach these base cases. In case of Fibonacci function of 0, it will return 0. If it's 1, it will be returning 1. Okay, so this can be also represented as follows. Like Fibonacci of 5, it will be recursively calling the Fibonacci function n-1 and then n-2. n-1 here, it will be 3, and then n-2 until we reach the exit. Here we have n-2, n-1. This will exit, but for this n-2, we have to call one more again, n-2, n-1. So this is the relationship between the subset of the problem. So this Fibonacci series problem statements can be expressed as a set of smaller number generation expression in terms of Fibonacci n-1 plus Fibonacci n-2. So now I was trying to understand the problem in order to build the program that can solve this problem mathematically, because I have now the relationship between the inputs and the expected outputs. I figure out that I have the three components of the recursive law. I found the base cases. Here I have the base cases where I can exit when the n value is equal to 0 or 1. And then I have also the recursive cases. So this leads me to the solution that will be implemented as follows, just to implement this expression here. So I define a function called Fibonacci with the keyword def. This is the header of the function definition, which will be finishing with the column. And then I have to check whether by receiving the value of n, the case base is satisfied for n equal to 0 or equal to 1. I have two cases. I have to check here if n is less than or equal to 0. In that case, I will return the value of n. And if n is less than or equal to 1, I will return 1 as result and then exit the function. Otherwise, I will go in else. I will calculate the Fibonacci of n-1 plus Fibonacci n-2. Those are the recursive cases. So I will be repeating until I reach one of those two cases, which are base cases. So here I have the base cases and the recursive case. I satisfy the law of recursion. So now let me build the function calling part. Here's the function definition. The function calling part is expressed as follows. I have the formatting of the results. Because here I would like to find the nth Fibonacci number of 4. So I will now then call the function by sending the value of n as a parameter. The output will be 3. So this will be like this. First, when I call the Fibonacci, it will go through the tests, and then it will go to the else case. It will calculate the Fibonacci of 3, and then this 3 will be returned to this function. And then this function, Fibonacci plus 2 and minus 2, it will be receiving parameter of 2. This will return 2 here to this function called, and then the second part will be receiving 1 as a parameter. This one will already satisfy the base case. Then I will just go with this last one here, which will also return 1 and 0. I will satisfy then the recursive base case condition. Then the final step will be just to run for 1 and 0 to exit the function. So this is the solution working step for the Fibonacci function I've defined earlier. As you can see, it's a function which calls itself several times. So that's why we call this function as a recursive function, which is a function which calls itself to perform task. Then there is a question about the use of recursion in Python. So in Python, we have a limit of the number of calls we can make, which is set by default to 3000. For a recursive problem, you have to make sure that the number of recursion do not fall beyond the depths of the recursion limits. So be aware of that, because if you don't set up that properly, you may face some cases of stack overflow where the memory cannot sustain the storage of the intermediary steps. This can lead to an error like recursion error because the stack has been full. There is no any space to put values. Then the recursive solution may be less efficient than iterative one, because recursive, as you can see, we need to keep in memory all the the intermediary steps, which may be costly in terms of memory. So be aware of that. So for you to check the size of the limits of the recursion, use just this instruction. First of all, you have to import the system module. From the system module, you can use the get recursion limits function. For this case, when I run this, you will see I have here defined the function. I import the function, the system module. From the system module, I use this get limits. You will see it gives me the default value is 3000. So I can only develop a recursive function that can make 3000 calls. Then you can also fix that limit by yourself. If you want to set a limit by yourself, for example, here is the method to fix the length of the recursion limit in your program. So in this case, I use the same module function, which is system. This time, instead of using get recursion limit, I use set recursion limit, and then I send the value of the limit. If you wanna set it by 10 recursion limit, you can set it by providing this value. So when I call this function with that argument value, you will see it will now be 2000 by default. This is very important to know as well. So now let me try to compare the iteration, okay, approach with the recursive approach. The iteration approach, we used loops, okay, like for loops or while loop, with all the variants we have learned. For recursion, you have only to use function. Iteration, you can use function or not. It's up to you. So by definition, the recursion is just a set. Okay, it's an iterative set of instructions that you have to repeat again and again using the loop. On the other side, for recursion, you have a function, okay, a recursive function, which has to call itself to repeat until the base condition is met, as I've shown in the earlier examples. In terms of code simplicity, the iteration is quite complex because you put all the code together. It can be messy to implement all the cases. And in terms of code simplicity, the recursion is quite clear and elegant to implement because it shrinks all the code in just a small block that can be called again and again. In terms of size, the iteration will have big size code. The recursion will have smaller one. In terms of performance, I've mentioned that several times. The recursion is quite slow because it takes the intermediary values. The iteration, it's used directly the memory access. That's why it's fast. In terms of memory usage, iteration is efficient. Recursion is quite heavy because you have to access to the stack. It has some stack access overhead, and then it can lead to overflow when you reach the limits of the recursion. Use cases, you can use iteration for counting, loops, or just simple sequencing logic. Recursion can be used for divide and conquer problem, where you can divide a problem in sub problem of the same types. Like tree problem can also be implemented with recursion. In terms of termination, in the iteration, you have a control variable. Okay, when the control variable value is fulfilling the exits condition, at that time you can exit the iteration. While in the recursion function, we have the base case condition. That's the condition to exceed the recursion function. Be aware, in both cases, you may face some issues if you don't set the exit condition properly. So this can lead to infinite iteration. So be aware of that, especially for a recursion. It can be severe where the system can crash because it lacks memory or resources. So this is what I can say about the iteration and recursion. Which one to choose? You have to stick to the characteristics of your problem statement, and then you can decide which one fit your case. So when to use it, remember that you need to use recursion only when you have a problem which can be naturally broken in smaller problem of the same time. Okay, so manage also the depths of the recursion code. If you don't manage that properly, it can go to a severe issue of stack overflow. And then the solution, when the solution use iteration, okay, by using iteration is hard to implement. In this case, you can use recursion. Those are some cases. I can elaborate on other few cases for recursion. Let's assume that you are given a multiple digit number like this 1, 2, 3, 4, 5, 5-digit number, and then they ask you to write a Python recursive function that can sum the digits of the number. Remember, this is different from the previous example. In the previous example, we receive a list of items, but this is a number, an integer number, but we want to solve the digits of the number. So for us to do that, we define a function called digit sum with the keyword def, and then it receives the number as n. First of all, we have to check whether the case base is satisfied. If n is equal to 0, in that case, we return 0. If not, we return n modulus 10, okay, plus the call of the function with n divided by 10. So we'll get only the integer part of the division. Then we will repeat again and again. So here's the function definition, and then here is the call of the function, which represents the body of the program. So it will be formatted as follows: sum of the number 1, 2, 3, 4, 5 digits, and then we call the function by sending this integer number that will be sent there as an argument value to run the recursive function. So this will be run again and again until we get the results. Here's the example. The result here is 15. But now I want to show it with the visualizer. You go to edit. You will see what is going on in memory. So again, at the first place, when I load the program in memory, the interpreter will point to the first line. It acknowledges the function definition, and then it stores that in memory as an object. Then it will go to line 7 here to the body where we call the function. It collects the argument value. You will see here is 1, 2, 3, 4, 5 as an integer. Then it will check whether the base case condition is satisfied. It's not satisfied. It goes to line 4 where it computes n modulus 2 plus the call of the function with n divided by 10. You see here the value of n is 1, 2, 3, 4 because we remove 5, okay, from the digits. It will go again, check whether the case base is satisfied, and then here we will have 1, 2, 3, 4. Again, it will compute n modulus 10 plus the call of the function with the new n. You see here the new n is 1, 2, 3. That will be passed to this function. Here we call again, we go back with the new value of n again and again until we reach the last step. Will be here. We have 1 digit. So in this case, we will be checking again the base condition. We have n, which is equal to 1. it doesn't satisfy, we go for the last round. So we will have 1 modulus 10, that will be 0 here. And then in this case, n is equal to 0. We take n divided by 10. And then we'll send that to the function, because we call the function here with the new value of n, which is 0. You see here, we check this time, this condition will be satisfied. 0 is equal to 0. Then we can return 0. Okay, look at now what is going to happen. We now collect all the intermediary results, okay, and clean the memory. Next, we see we return 0 first, and then the previous round value 1, the previous round was 2, 3, 6, and then the final step will be to send back the final results, which will be sent to the calling body instruction. And here the result is 16. Yeah, I think this makes sense for you. You can visualize how the program is working. The last example I'm going to give is how to calculate the greatest common divisor using the Euclidean algorithm. Most of you are familiar with this problem, but this problem of calculating the greatest common divisor using the Euclidean algorithm can be mathematically expressed as follows. The GCC of x and y is equal to x if y is equal to 0. Or the GCC x of x and y is equal to GCC of y remainder of x and y if y is greater than 0. So you will see we'll be repeating this case again and again until we reach the base condition, which will be x when y will be equal to 0. So by end, if we calculate, you can take, for example, we try to find the GCC of 12 and 15. We'll divide 12 by all the divisor until we reach to 1. So 12 can be divided by 2, which will give 6, 2, 3, 3, 1. 15 on the other side will be divided by 3, 5, 5, 1. Okay. So what is the common elements from 12 and 2? It's 3, which is common for 12 and 15. Then the greatest common divisor of 12 and 2 will be 3. This is the computation by ends. So how can we tell the computer to do that on our place? So first of all, I have to make the algorithm of the solution to this problem. So the algorithm can be expressed as follows. Just another way of representing the mathematical expression I've explained earlier. I need a function which will be called GCC, okay? And then I will define what could be the parameter that could be given as the input. I need to take x, which will be of type integer, and then y integer. Then I have to check the condition such that x should be greater than 0 and y greater than or equal to 0. If this condition is not satisfied, directly this will be the base case. I will return basically the results as the problem it's defined. Then I will start. My function will have only 2 lines. The first time I have to check whether y is 0. If it's 0, I will return x. In the other case, I will return GCC of y and the remainder of x divided by y. I will repeat this again and again until I reach this first base case condition. So now it's clear. I can now build my Python function. You can see it's just few lines, quite simple. I have the function definition here. Def GCC is the name of my function. You have to make sure that GCD is not a reserved keyword. It will receive 2 parameters, A and B. And then I have to check whether B, which is equal to Y in my pseudocode. If B is equal to 0, then this will be the best base case to exceed the function. Otherwise, I will return B and the GCC of B and A modulus B. This will be repeating again and again until I reach this condition. This is the function definition, just 3 lines. And then I have the body where I call the function. So I would like to print the result as follows: GCC of 48 and 18 equal to, I call the function here and sending the parameters. So it will be outputs the result as follows. Then my code here, when I run it, you will see the result is 6. So now I will elaborate on the types of recursion in Python. So we have figured out what is recursion, what are the 3 laws recursion solution should follow. Like recursion function should have 3 components, includes the base case, recursive case, and unintentionally management statements. So those are the 3 laws to follow when you have a problem that can be broken down in some small sort of problems of the same type. So in terms of writing the same code again and again, so you can just write once a function and call it as a recursive function to solve the problem intermediary, and all the intermediary results will contribute to the overall problem solution. So now I will elaborate on the types of recursion supported in Python. So we can mainly classify the recursion in few category depending on the position and the nature of the recursion call within the function. The second aspect of the recursive function classification is how many the function are called in the recursive relationship. So these are the 2 main criteria we use to classify recursion. First, the position and the nature of the recursive call within the function. Second, how many functions are involved, okay, in the recursive relationship. So we can categorize mainly in 2 types. We have direct and indirect. Then the direct types of recursion can be further categorized in 4. We have tail, head, tree, and nested. I will be now elaborating on each of these types of recursion with some example to give a sense to each of these recursive type. Let's start with the direct recursion. The direct recursion is a function call itself directly to solve a problem. So when the call is directly done by a function itself, this is a kind of a direct function. So as a subset of direct function, we have the tail recursion. The tail recursion is a type of recursive call which is made in the last statement of the function. When you have a recursive function and the last call is to call the function itself, this is categorized as a tail recursion. So there is no operation which is performed after the recursive call is made. Like most of the examples we have seen, we use mostly the return line to call the function. It was mostly the last line. So those are kind of tail recursion. And the idea is for conversion into loops. If it's like that, you can convert that in the loop. It will be easy implemented in the loop. As we have mentioned, the loops are more efficient and they use less resources. Although in Python, they don't provide any optimization approach for tail call. So be aware of that and choose the best way to implement that. With an example, here is a tail recursion function where we have the last line, which is used to call the recursive function. You can see the function is defined using the QLDEF, and then we have the parameter which is sent as an argument through n. We check whether the function include the base case. The base case is here. If n is equal to 0, it will return nothing. That means this is the best case, the base case. And then else, if the condition here is not satisfied, that means we should go to the recursive call. Before that, we print the value of n, and then we can call the function with n minus 1 until we reach the base condition with the value of n, which is equal to 0. This is the part of the function definition, and then we have the part of the function call, which is the main program or the body of the program. We have to print the results that will be returned by the tail rec function. So this will print an output like it will be counting from 5, 4, 3, 2, and 1. So with that, let me show you the codes, how it works. This is the code of the tail rec function. When you run this code, it will count from 5 to 1. And you can see here the last call is the recursive call statements. This is the type of tail recursion. The second type of direct recursive call is the head recursion. This recursive call happens first, okay, and then it is followed by operations to perform after the call is returned. So when we first call the recursive function, this is a type of head recursive, and this is used for the execution that will move deeper before any result is proceeded. As an example for this, we have this function which call first the recursive function in case the base case condition is not satisfied. So we have the function defined here with the keyword def head record function, which has parameter n, and then it check first for the function to work. We have to identify the case base. So if n is not equal to 0, that means we call first the function itself. This is the head recursive. So the first operation we are doing after checking whether the case base is existing, we call the function, okay, the recursive call before the processing. Then we process n, okay. Then the print n will be processed after running the recursive function call. This is the part of the definition, and then in the body of the program, we call the function within the print function to print the result when it will be sent back by the function. The output will be counting from 1 to 5. It's almost the opposite of what we have seen in this tail function, where we process first the operations and then we call the recursive function later. But here we call the recursive function first and then we process other operations. This is the head recursive. With the code, when I run it, you will see here the result is the one accepted. Okay, 1, 2, 3, 4, 5. This is the expected results. The third type of direct recursion is the tree recursion. This type of recursion is for function that's call themselves multiple times. When a function call itself multiple times, this is a type of tree recursion. It's like in the problem we've seen for Fibonacci or for permutation or combination. Such kind of problems are organized as a direct recursion, particularly a tree recursive function. As an example, to add to what we have seen earlier, we have here a tree rec function, which is defined taking a parameter called m, and n. When it's equal to 0, this will be the base case, will return nothing. And if the best case is not met, we will process the remaining instruction or statement in the function. We will print the value of n, and then we'll call the recursive function with n minus 1. Then we call it with n minus 2 until we reach this base case condition to exit the function. This is the part of the definition, and then in the body of the program, where we call the function, we have just to provide the function call by calling its name and sending an argument value that will be passed to the function and received by the n variable. This will print like this. So remember that we have mentioned one of the problem with the tree recursive is the limits, okay, of the depths we can support. For Python, by default, we have seen that Python accept up to 3,000 calls. Such kind of statement here, you will see it will be looping again and again until it reaches the maximum. Okay, now look at this. It's very important to understand. Let me first clean up all the outputs. Okay, with this example here, look at what's happened. You see, it's run again and again, and then it will reach the maximum of call. It's calling several times. You can see the result is going again and again and again until it will reach the maximum. Here you will see it will still calling itself, and here you will see it reached the maximum, and the stack does not have resources. When it reached the maximum, it will show the message like maximum recursion depth exceeded. So that means you didn't manage properly the number of recursion. This will be critical and cause the system to crash, like in this case. So you don't have to do that. But in order to fix this problem, you have to manage the depths. Like here, this condition will always be true because n, when it reaches 0, it will not be changing again. So this condition will be always true when n is equal to 0. So in order to fix that issue, we can stop the recursion by fixing the n to be less than or equal to 0. When we change the condition like this, we can stop that more effectively. When I run this version, you will see here, everything is controlled by this statement here that is used to check the base case. So if you don't set properly the best case tests or condition, it will be difficult for you to exit this function. So make sure you please be muted.
我没开麦吧？
So make sure that you control very well the exit of the recursive call by setting up properly the condition. Like in the previous case, you have seen we didn't have a proper setup of this condition. It went until it reached the depths of the recursion call, which is set by default in Python to 3,000. So in order to avoid such kind of situation, make sure you set properly the condition of the base case. The last, in the type of direct recursion, where function call themselves to solve sub-problem or intermediary step problems. Here I have already explained through the example. So this was the statements which help us to control the depths of the tree. The next type of direct recursive function is the type of nested recursion. So this is a type of function where a function recursive call itself contain other function recursive call. Okay, so this is the most complex one. If you don't build properly your algorithm, it will be difficult to control such kind of nested recursion. When you are facing such kind of situation, you have to be careful when you set the the base case statements. Otherwise, it will be difficult. So here's an example of the nested recursion, where the function is defined with the keyword def, and then we have nested rec, the name of the function, that will receive an argument n, which is defined as a formal parameter, and then we check whether the case-based condition is satisfied. If n is greater than 100, if it's so, it will return n minus 10, okay, to the calling line. Else, if this base case condition is not satisfied, we will go to the else part. The else part will be calling the function itself. And then inside the call of the function, you have another function call. So you have a nested call, a function which call itself like this. So two functions that need to be performed together. Like this, first of all, the inside call will be performed, and then the output of this inner internal call will be given to the external call. You will see this is kind of complicated. If you do not set properly this condition, it will be difficult to deal with such kind of situation. Here was the definition of the nested recursion. And then the call of the function will happen in the main part of the program or the body, where we call the nested rec function by sending the parameter value, which is 19. And then it is called inside a print function to print the result as soon as the result is sent back to the instruction that is called the function. I will show you live, like this one will be working like this. You have, here's the results. It will be counting down from 5 to 1. And then the last round, it will be none, because the, no, here, I'm mistaken. Here's the example. The result will be 19. Then let me show you in the visualizer how the Python interpreter is interpreting this program. We have a nested call of a recursive function. First of all, you remember when you load the program in memory, the interpreter will point to the first line, and then it acknowledges the structure of the function. You see the object here is a function, and then it says to receive a parameter, which is n. It is set up in the global memory. Why? You remember last time I discussed the difference between the global namespace and the local namespace. So this global frame is the global memory where the global objects are stored. So local scope objects will be inside the function here. They will not be accessible to the global space. Then it goes directly to the place where the function is called for the first time. It's line 7. When I call this function, it will go back and forth until the base condition is met. So next, it will take the argument which is passed to the function, which is memory. You will see here rec. They will pass the 95 as an argument to n in memory, global memory. Next, it will check whether the base case condition is satisfied, which is not satisfied. 95 is not bigger than 100. We'll go to else. And then else will be the nested call. Look at now what is going to happen. It's very important to understand. Next, look, it will take now the current value of n, okay? The current value of n, which will be, that means it will process first the inside call, okay? It will take first 100 plus 95 plus 11, it will be 106. And then it will call again the function, okay, by sending 106 here at the line number 1. You see here, it will check whether 106 it's greater than hundreds. Now the base case is satisfied, okay? What will be the next step? It will be returning the value. In this case, it will take now the current value of n, which is 106 minus 10, it will be 96. Then it will call now the external function here. This is now 96 as a parameter, which will call the external call. It will send 96. 96 is below 100. It's call again the function again and again until the last step will be reached. It will be repeating until we reach the base. Until we reach the base. Now is 99. Again, it will take this 110. Again, hundreds. Okay, now it's hundreds. Okay, look at now. We send the external call with hundreds. Okay, when we run again, it will not satisfy because 100 is not greater than 100. It will go again to the recursive call. It will be now plus 11, 111. Then it's call again. It will be 101. In this case, 101 is greater than 100. The condition will be fulfilled. Here, we can exit now the function. You can see here, everything is happening in memory, in the global memory. I have already loaded the function in memory, so I don't have to read again the code again and again. So this is like, for this problem, you have to repeat again and again the same code. If you use the normal implementation, it will be messy. So it's allowed you only to implement it once and use it when needed. In this case now, we can exit. N is 101. Okay, we check the condition is satisfied. Then we can run the line 3. Okay, at this time now, we will now collecting all the intermediary results. Look at now, we return 91, which is the value. Then we clean the memory, and the final result will be 91. I hope it's clear. This is what the interpreter does in order to provide the 19. On the other side, we have another type of recursion, which is indirect recursion. Is in the case where a function calls another function, which eventually call the original function back. Okay, this is such kind of particular cases where we have indirect functions. Like you have a function a, which has an argument or parameter which is n, and then the base case is to check whether n is greater than 0. If it's so, it will print the value of n and then call another function b. Then the second function b is also defined almost similar with func a. The condition-based statement is same, n greater than 0, and then print. Here we divide n by 2. We just collect the integer part. This is the definition of these two a and b functions, and then we have the core or the body of the program where we call them. We just call a, and automatically a we call b. This is kind of indirect call. B has never been called in the main program. So here is the case of indirect call. So A was called, A called B, B called A, vice versa, like this. And then to show you how it's work, I think this is where it's good to see here in Jupyter Notebook, you just see the results. I would like to show you the steps. The steps is good to understand. I use again the visualizer here to give you the steps. Look at here the difference with the other cases. Okay. In this case, when you launch the program, automatically the program will be loaded in memory, and the interpreter will point on the first line. It acknowledges the existence of a function called func a that will receive n as a parameter. Automatically, it knows what is the inside logic of this function when it's loaded in memory. Then directly it goes to the next line. Here's the next line. It's also a function definition. It's acknowledge the existence of a second function, which is func b. It's also load that in memory. You see, I have global memory where I load an object. This is a sub program that contain instructions, and those instructions they use variables. So it use memory. Okay. Then next will be to go find the first place where let me go back previous. I'm here. Next, after acknowledging the existence of b func b, it will go to find the first place whether a or b is called. Here is the part in the main program where the function a has been called. Okay, it's now acknowledge the call. It's take the value which will be sent to the function a. It will be stored in a as a memory, and then it will first, okay, go and point to the previous function that was in memory. It was b, but here we call a. It will go find a in memory, func a in memory, and then func a will return this value 5, and then when func a send value of n 5 to b, b will receive that value here, and then will return the 4 divided by 2, that will be 2 value of n, that will be sent to func a, and then it will go back and forth until the condition is fulfilled. You see here the condition is 0 for this the third call of a, and then here n is equal to 0. That means n is no longer bigger than 0. That means this case will be fulfilled, is the base case. Next, in this case, we collect now, okay, because the next step there's nothing, but we found the last value of n. Now we will be returning the intermediary values. Next, we collect 0, we collect 1, we collect 2, we collect 4, then we collect 5, and then nothing. So we'll be printing the intermediary values like this: 4, 5, 5, 4, 2, 1, and none. None will be the last call with the value of 0. I hope it's clear. You see how the Python interpreter understand such kind of logic. So let me now give you a sense of comparison of these 5 types of recursion calls. We have the direct recursion, okay, which has 4 subtypes. We have tail recursion, add recursion, tree recursion, and then nested recursion. On the other side, we have indirect recursion. So for tail recursion, which is a kind of direct recursion, where the recursive call is the last statement, okay, in the function, and it can be used for counting down or for summation use cases. In the second type of direct recursion is head recursion, where the call is the first operation after checking the base case condition. This can be used for backtracking or reverse printing. The other one is the tree, where we have multiple calls per function. So this can be used for Fibonacci series generation or binary tree search, for example. The last in the row of direct recursion, we have the nested recursive function where we have recursive call inside other recursive call. So this can be used for most complex problem like the MC CART19 problem or the mathematical puzzle. Last but not the least is the case of indirect recursion where we have multiple calling between two or more functions. This can be implemented for alterating logic. So depending on your use case, you can choose which recursion approach to implement. So as a summary for recursive function, we have several types of recursive function. You have to understand each of them in order to make your choice. Remember that for recursive function, we use the memory flow. Everything is going back and forth in memory. So be aware of controlling the depths of recursion. Otherwise, it will be facing some stack behavior like overflow situation. And then it's better to use efficiently the memory or resources. And then choosing the right type of the recursive function, it may be also challenging, but this can be figured out from the nature of the problem you are facing and the expected order of output that the function has to give back. So remember that tree and nested function can be more complicated. When you use them, you should be able to build properly the base case condition. Otherwise, it will be difficult to exceed the recursive function. So just to sum up, I can say that recursive function that's called themselves. And for you to build a recursive function, you have to satisfy the three laws of recursion. You need a base case for the stop or exit of the recursion. You need a recursive case where the function call itself. And then in terms of use cases, they can be used for factorial, Fibonacci, tree, graph, such kind of repetitive operations. And remember that Python by default has a limit of 3,000 calls. If you have a deep function call, you better figure out how you can control that. So the best choice is to choose the appropriate recursion type, but it's not always easy. But always try to define the base case. This is the most important part to enter and exit the function. Ensure that the progress throughout the intermediary calls is not infinite. So this can be controlled by the condition you set for the base case. And then optimize the memory usage, okay? The memory usage is very important. So you can use memorization by using some Python module defined function like the LIU cache that can be also useful for expensive recursive calls. So consider using iterative solution more than recursive function in critical application. But if you cannot define your recursive problem, your iterative problem in terms of a set of sub problems that can be of the same type to use recursion, is better to rely on the recursive solution. So this is what I prepare for you. Write a Python recursive function to compute the sum of the first 5 natural numbers of a user given integer number. We have solved somehow a part of this problem in the examples, but here the particularity is for the first n natural number of a given number. So as example, we have sample inputs. The inputs should be like enter a number when the user provides 10 as an input. The expected output will be the sum of the first 10 natural number is 55. So I have first to understand the problem statement. So since we already figured out how to compute the sum of numbers using recursive function, I can start first by defining the function. Okay, I can use keyword def, and then I say sum n for natural number. That will receive a parameter as n. Then this header line has to finish with column. You see, automatically I have indentation. Okay. Then I have to check for the base case. I have to check if n is not equal to 0. If n is equal to 0, what do I have to do? I have to return 0. Else, this is the base case for me to exit the function. So if the base case condition is not satisfied, what do I have to do? I have now to return the number, the value of n plus n minus 1 until I reach 0. Okay, you see, it's easy now. Now, in this, I have return. I will return n. That's the current value of n. Then I will call again sum n with what parameter? The parameter here will be, because the value of n has to change. The parameter here will be n minus 1. Because if I don't change the value of n, I will never satisfy this statement here. Okay, that is the end of my function. And then I have to call the function. Okay, function call here. Okay, I will call the function here. So what do I have to do for the first time? In the input, they say I have to show the message enter a number. How to do it? We already figured out how to write an input statement. I need a variable, which is n. And then n should be receiving integer value. How to cast the type of the given variable? I have to use int function. And then inside int function, I have to use which function to get the input is input function, which has to prompt which message. They have shown me in the input sample. I have to show the message enter a number. Then like this. Okay, that is the input statement. Now I need a statement to call the function sum n and then format the output as it has been shown in the expected outputs. I will use print, and then inside print, I have to format the print. I use the format style f with f. Then I have to print the message, the sum of the first. I have to collect the value of n, and then natural numbers is column. Then I have now to call the function outside the text. Okay, and then for that I need to put comma. Then I will call sum n. This is the name of the function. What do I have to send? I have to send n as an argument that will be storing or saving the value provided by the user. This is the solution to my problem. Let me test if it works. Shift enter. It worked so far. They say I have to provide 10. I provide 10. Then when I hit enter, it worked properly. That means I have solved the problem successfully. It mapped the expected outputs. I solved the problem using recursive approach. This problem can also be used by using iterative approach. I can only use a for loop or while loop. But in this case, if they ask you to use a recursive function, it's quite simple. If I use a for loop, it will be more than this. It will be maybe having 10 lines. But with recursion, I use only 3 lines here to define my logic. And you see it's quite simple and elegant. So this is the solution to the first problem. Any question? Yeah, we still have 10 more minutes. I take the second one. The second question or problem statement say that write a Python program that prints numbers from a user given n integer number to 1 using recursive. It's like what to use the for statement with iterative approach, counting down, okay? But now we do not use any for loop instruction or while loop instruction, but we use we have to use the recursive solution. So how to do that? We have to count in the ascending way. Okay. I will take my keyboard and then try to reformulate this problem statement to meet this sample inputs, and then the output will be like this. We have seen in the example a similar example. So let's now try to adapt to this use case. So first of all, I have to define def my function. Def, I have to print, okay, prints numbers, okay, counts. Okay, I can call it like this. You can call it wherever you want. The problem is to get a result. Then this print number counts will be receiving a parameter that will be sending a variable value arguments from the call. And then I finish with column. When I hit enter, it will indent the cursor. And then I have first to check for the base case. I check whether n is equal to 0. If it's so, I will return nothing. Okay, because the problem statement say I have to count from n to 1. So in the other case, what do I have to do? I have to call the function. So in the prints, I will prints, and inside I have to call the function prints number counts. Then in this case, I have to provide the arguments that will be n minus 1. Then I have to print now n in this case. You remember this is which kind of iteration? Where the call is performed before the proceeding. Which one was this type of iteration? When the recursive call is done first, it will be the case of add recursion time. If it's done last, it will be the tail recursion. In this case, we are in this case, head recursion, where we call first this function before proceeding with any other operation. Let me now write function will be called here. Here's the place I will call the function, and the function before the call of the function, I have first to collect the input from the user. It will be same like in the previous example. Int, I cast the value of the inputs, and then I use the inputs function to collect the input from the user, enter a number like this. Then I will now call the print number count inside a print, okay, just to print directly the result as soon as I receive the result from the function called print number counts. Then I have parentheses. In parentheses, I have to send a parameter, which is n. Okay, this is the end of my solution. Let me check whether it's correct or not. If it's not correct, we can debug that. So far, so good, it works. It's asking me to provide the inputs. In the sample, they say I have to provide which inputs? 10, for example. When I provide 10, it will count from 1 to 10. this is the ascending way, okay? If I have to count in descending way, I have just to change the place of this print and put it before. For the tail case, it will be working as expected. You see how I fix it? So this is the correct one. It should be a tail recursive function. I hope I've provided enough details to help you understanding the concept of recursion, how you can define a problem as a recursive solution, and how you can build your recursive solution using Python as a programming language. I hope it's clear to everyone. So I'm expecting to check that through the assignment you are going to submit.